Billy Edge. I'm with the Coastal Studies Institute here at UNC, and I would say that I'm also director of the Renewable Ocean Energy Program that we have here at CSI, which is connected with our engineering institutions in the state. It's my pleasure this evening to introduce Mr. Jonathan Colby. And Jonathan comes to us from Verdant Power, where he is the director of performance evaluation for the technical products and a hydrodynamic engineer. He comes to Verdant from Georgia Tech, where he earned a master's degree in aerospace engineering, and before that from Berkeley, California, at the university, where he earned a Bachelor of Science in Mechanical Engineering. I'm very pleased to say that he has moved from aerospace engineering into hydrospace engineering, and we're all going to be benefit of that. In 2012, the American National Standards Institute awarded him the honor of the Next Generation Award, meaning that he is a mover and shaker and a rising star that we'll be looking at for some time in the future. I'm also pleased to say that he's not only a colleague, but a good friend, who I've had the opportunity to work with not only here on the technical advisory board of our Marine Renewable Energy Program, but also on a number of standards activities associated with marine energy. This evening he's going to be talking about the marine industry and what we're doing offshore in order to affect a little more renewable energy that comes from that tremendous resource we have in the ocean. Jonathan?
Thank you very much, Billy. Good evening, everyone. I'm Jonathan Colby, Director of Technology Performance with Verdant Power. And as Billy said, I'll talk tonight a little bit about the marine energy industry, share some global progress, and talk about some opportunities for the state of North Carolina. Again, thank you very much for coming. It's quite a brisk evening here in the Outer Banks of North Carolina, so I certainly appreciate all of you braving the elements this evening. Would like to also welcome everyone who is watching this online. Thank you very much for joining, and I hope everyone enjoys my presentation. In brief outline, I'd like to talk a little bit about my company that I work for, Verdant Power. I'll move into an overview of the marine energy industry, and there are a number of sectors in the marine energy industry. I'll talk a little bit about the tidal energy and energy from currents. I'll talk a little bit about the opportunities and progress in wave energy, and then I'll talk about a couple other forms of marine energy that are out there that people are investigating. I'll focus then on what's going on specifically in North Carolina, in particular the research that's going on in conjunction with the Coastal Studies Institute here, and then I'll finish with some opportunities for North Carolina as we move forward. To start and give a little perspective on what marine energy is, I wanted to show you all a picture of the Verdant Power deployment of a tidal energy turbine in New York City. So here you can see the turbine in the bottom center in blue, and you can see some of the ancillary support vessels that we need, including the spud barge, tugboats, work vessels, etc. In the background, you can see the 4 large smokestacks of a conventional power plant, and so you can get a sense of the scale of what we're talking about here. And so while we are smaller than a large power plant, for example, we do use some pretty heavy equipment in these marine environments. If you zoom out from that image, Verdant Power's main project is what's known as the Roosevelt Island Tidal Energy, or RITE project. The RITE project is located in the east channel of the East River. So what you're looking at here is an overview of New York City. On the left side is Manhattan, on the right side is Queens, and in the middle is Roosevelt Island, which separates the East River into 2 channels, the East and West Channel. Inside of the red circle, you can see the 3 buoys that demarcate the Verdant Power RITE project. And so this gives you a little geographic context of where we are here in the United States. Looking at Verdant Power, we were established in the year 2000 in New York. We've developed a technology called the Kinetic Hydropower System, or the KHPS. We do have global ambitions, and so we've established a number of companies abroad, including in Canada, in Ireland, the United Kingdom, and also in Asia. Looking at the evolution of our company, there's an acronym there that you may not be familiar with, which is TRL, stands for Technology Readiness Level. This is a metric that is used to quantify the development of technology from sort of back of the envelope at a TRL 1 up to a fully commercial product at TRL 10. And so you can see we started off in a proof of concept mode about 10 years ago. We advanced that technology further through the full-scale demonstration at the RITE site. During that period, we operated 6 turbines simultaneously. It was the first ever grid-connected array of tidal energy devices in the world. You can see in the upper right corner the Gen 4, or 4th generation technology that we demonstrated in New York. In the lower right corner, you can see the 5th generation, or Gen 5, which we consider to be our commercially ready technology. In comparison, you can see some of the differences, including in the shape of the pylon, the shape of the blades, etc. So lessons that we learned from the demonstration project in RITE fed into the engineering design of what we consider our commercial project. As we move forward, we look to really build out the commercial project in New York in the next year to 2 years. And I'll talk a little bit more about that as I go along. And another exciting development for us is on the river energy front. We recently were awarded a large contract in Turkey to examine using our technology downstream of dams to capture some of the energy that was not captured through the dam in the downstream river. And so we see some very significant global opportunities. And so I'll share a little bit about where the US is, share a little bit about the global opportunities, and then finish, again, as I mentioned, here in North Carolina. A little more perspective of how Verdant approaches this, so you can get a sense of how a real equipment manufacturer considers the problems. When you look at developing a project, we see 3 main components of that project development to be successful. The first, you have to advance the technology itself. You need robust machines, highly efficient, perform well, etc. At the same time, you have to really evaluate cost-effective manufacturing, installation, and operation and maintenance. As I think most people know, any work on the water is very expensive and comes with significant risk. And so it's a very critical piece of a successful project is to minimize the cost, time, etc. on water. The third and equally important piece for a project success is the confirmation of its environmental compatibility. As you know, most renewable energy systems face concern over the environmental impact. Wind turbines have had birds and bats. In the marine case, you have fish, mammals, endangered species, etc. And so what I'll talk a little bit more about is our FERC license. And in that license, we really show quite definitively the environmental compatibility of our technology. And so in that license, I'll talk a little bit more about it, but you can see an image of it here. This is an overhead view in the bottom of the east channel of the East River. The triangles you see represent 3 turbines each. And so that's the full array of turbines that we plan to build in New York. To do that build out, we need to continue to monitor the environment. To do so, we propose to the federal government a suite of monitoring protocols that we call the RITE Monitoring of Environmental Effects, or RMEE plans. An innovative step that Verdant made was to identify specific flow scales. And with a flow scale, there are very specific questions that you can ask and very specific technologies you can apply to answer those questions. Those 3 scales are presented here, and they're relatively straightforward. You have the micro scale, which relates to the interactions of fish species around a single turbine. So you can imagine here you have issues with a rotating blade, for example. Are fish being struck by that blade? Are fish interacting with this machine in some way that's adverse? An example of what that would look like is shown in the black box. That is an instrument called a DIDSIN. It's a high-resolution sonar device, and it's used to image fish. So what you see here, albeit it might be a little difficult to see, is a school of fish that was imaged using this DIDSIN. So this is an example of a micro-scale tool that you can use to image individual fish and monitor their behavior in and around an operating machine. If you go to the next scale, or the mesoscale, you're looking at impacts within an array. So you're no longer looking at a single machine impact, but you're looking at the cumulative impact of multiple machines as fish or marine mammals attempt to navigate through that channel. So here you're looking at changes in fish distribution, changes in usage of the channel, for example, and potentially changes in some predator-prey dynamics. Finally, you look at the macro scale, which is beyond the array, looking at a much larger reach of the entire river ecosystem itself. And so on the right, you see an example of what's called the New York Bight, which is an interconnected set of waterways, ocean, etc., that fish use in their migratory and residential life. One of the critical species of interest in New York is the Atlantic sturgeon. That fish is shown in the bottom right corner. It is on the endangered species list, and the environmental hurdles are ratcheted up significantly when endangered species are involved. In this case, a very good example of macro-scale monitoring was the use of our company in a network of tagged species. Taking advantage of fish and marine biologists who tag Atlantic sturgeon throughout the eastern seaboard, we installed receivers that listen for those tagged fish. As the fish use the East Channel, our receivers pick up those pings from the tags, and we are able to identify the species of interest as they travel through the area. Atlantic sturgeon are known to migrate great distances. We have detected sturgeon that were tagged from as far south as Virginia, tagged along Long Island, and up as far as the sort of Connecticut and Rhode Island area. So as you can imagine, that's a much more macro-scale issue, looking at how Atlantic sturgeon migrate through this channel from quite significant distances south or north. And so hopefully that gives a little flavor of some of the different monitoring environmental concerns that we have and some of the methods you can use to tackle those problems. Excuse me. So that's about what I would like to say on Verdant. And so now I'd like to move to a much broader perspective of the industry in general. So I'd like to start in the US, and as a technology developer and an engineer, I will focus mainly on the technology, projects, and test facilities that are available in the world. Starting here in North America, you see a number of different project and technology developers represented here. I think one critical piece is to notice the real divergence in the technologies to capture tidal energy. In the lower left, you see the Verdant Power turbine, three-bladed horizontal axis machine, looks very similar to a wind turbine. If you look to the right, ORPC is another American company that you can see uses a completely different technology, what's known as a Gorlov or helical turbine. Looks quite similar to a lawnmower blade and a conventional push lawnmower. Very different technology, but an equal solution when it comes to extracting energy from the tides. In the upper left, you see a company on the west coast of America called Aquantis, which again is using the three-bladed horizontal axis. However, they've changed the mooring and deployment system significantly to where they're using a dual rotor on more of a floating type of platform. If you look to the upper right, you see a company out of Canada called Clean Current that takes advantage of a duct to provide a small amount of flow acceleration before it hits the rotating machinery. And so, unlike the wind sector and unlike the solar PV sector, you see a very broad range of technologies being explored to extract energy from the tides. In the US, if you would like to produce electricity from the tides and sell that power, you need a license from FERC. FERC is an acronym that stands for the Federal Energy Regulatory Commission. And right now, currently in the US, there are 2 licensed projects by FERC for the production of tidal energy. The 2 projects are the Roosevelt Island Tidal Energy Project that Verdant is conducting. As I mentioned, there are 30 machines shown here in the 10 triangles. The rated capacity of that field of turbines will be 1 megawatt. A second project is underway in Maine. This is being done by the Ocean Renewable Power Company, or ORPC. They were the more lawnmower blade technology that I showed in the previous slide. As you see in the upper corner of their figure, their project is near the Canada-Maine border, and you can see sort of the project outline. And so these really are the 2 showpiece, commercially licensed projects here in the United States, in New York and in Maine. If we look to Europe, Europe is the leader in this industry. They have more technology developers, and as you'll see, they have much larger projects, etc. Looking at some of the technologies, you can again see the pretty significant differences in the types of technology that are being deployed. You can see some of them use the 3-bladed horizontal axis concept. You can see the open hydro machine uses a duct with an open inner rotor. And you can see on the upper left, the marine current turbines utilizes a 2-rotor, 2-bladed system. So just really wanted to share sort of the range of technologies you can see. Another important piece of what's happening in Europe, which has not yet happened in America, is the large multinational engineering firms becoming interested in buying these companies, for lack of a better word. And so you can see, for example, the company MCT out of the United Kingdom has been purchased by Siemens. You can see the company Atlantis Resources Limited out of the UK is now in a partnership with Lockheed Martin. You can see that in the UK, the TGL was purchased by Alstom And you may or may not know that right now Alstom's power and energy divisions are in negotiations to be purchased by General Electric. So quite soon GE will be a player in the tidal energy industry. And you can see Open Hydro's device out of Ireland. DNCS is a French large engineering corporation. So we do see some of the large multinational firms taking an interest in this industry and starting to invest heavily in the technology, which, as you'll see, there'll be other indicators of the commercial viability of this industry, but this is absolutely an important step in proving the commercial viability of this industry, or to see some of the large players taking such an active interest. Looking at projects in Europe, I'll focus specifically on the United Kingdom and waters in and around the UK. You can see the UK in the middle, Ireland on the left. There are 4 projects that I highlight for a number of reasons. In the upper right, you see the Maygen project. Incredibly, they have allowed for up to 400 megawatts of tidal energy development at that one site to the north of England. Initially, 86 megawatts have been consented, but the maximum project size could reach up to 400 megawatts. If you remember from the previous slides, in the US, the largest project in the US is a 5 megawatt project, with the Verdant project only a 1 megawatt project. So you can see the scale of development is completely different in the United Kingdom when they're looking at these hundreds, potentially, of megawatt scale projects. Looking at the southern part of England, off of the Isle of Wight, there's a site known as PTEC that's looking to develop a 30-ish, 20 to 30 megawatt farm of tidal turbines. Looking off of the Welsh coast in Pembrokeshire, there's another project that's been permitted for up to 10 megawatts of power. And one of the newer projects, which is actually coming out of France, but is in the English Channel between France and England, is the Race Tidal Limited, which is potentially up to a 300 megawatt project in those waters. And so just a quick math, you're looking at close to a gigawatt of tidal energy potential, 750 megawatts, where in the US right now we're talking on the order of 5 megawatts. So really different scale of development when you look at what's going on in the UK versus what's happening in America. Looking in Asia, because Asia is also very, very interested in this, I highlight a couple countries and a couple of the different technologies here. Looking at China, you can see a couple examples of tests and prototypes that the Chinese have developed, both of which are floating devices. So if you look on the left, you can see a schematic, engineering type drawings of those devices. And then on the right, you can see them actually in operation. So in Japan, we have Kawasaki Heavy Industries, which is investing heavily in the development of a 3-bladed horizontal axis turbine. And then in Korea, you have a broad range of tidal current devices, but you have a different type of tidal energy conversion, which I don't really mention here, which is called a tidal barrage. A tidal barrage is quite different in that in this case, they take a bay or lagoon that has influences from the tides, and they build a large dam around that entire lagoon to enclose it. As the tides come in, they open gates in the dam that allow the water level inside the lagoon to rise to the same level as the high tide. When the high tide is reached, they close those gates and they allow the tide outside of the dam to ebb away. At the end of that ebb tide, you have quite a significant tide height difference. Inside the lagoon is high tide, outside the lagoon is low tide. At that moment, they open a different set of gates that let the water run through turbines and capture the built-up potential energy on the other side of that dam. As you can imagine, there's some potential ecological impact. Ecosystems in a lagoon tidal estuary usually count on significant flushing of water in and out through every tidal cycle. And so when you dam up that natural ecosystem, there are some pretty significant environmental impacts. And so you'll see in the US and in Europe, there's a lot less appetite for this tidal barrage concept, but there are some countries in the world that are interested in that idea. So now transitioning to wave energy, you're going to see an even broader array of types of technology available in the wave sector. So starting here in the US, we have a few examples that I'd like to show. On the West Coast, you have Columbia Power Technology based out of Oregon. In that upper top image, you can see a schematic of the rocking action that the two edges do as the wave passes back and forth. That rocking motion is converted into mechanical energy, which can then be turned into electricity. Looking on the right, you have Acilla Power, another West Coast company. This is what's known as a point absorber. And as you can imagine, as each wave passes, the top yellow buoy rises and falls. That rising and falling motion can be converted into electricity. On the lower left corner, you see a company called Resolute Marine. They have an intimate connection here in North Carolina, and I'll talk a little bit more about that. They're a Boston-based company, and they use the surge principle. And so that is this large flap, you can imagine, flaps back and forth as each wave passes, mounted on the bottom of the ocean, and just flaps. That flapping energy itself can be turned into electricity as well. So here are some examples of what's going on in the US regarding ocean energy, waves specifically. When you look to Europe, you can see, again, quite interesting technology concepts. In the upper left with aquamarine, you see a similar surge device. You can see people standing at the bottom. It's quite a large device. We're talking about pretty massive infrastructure here for deployment, maintenance, etc. If you look on the bottom right, this is the WaveStar device. This, again, is a point absorber. This one reminds me of a centipede. And as you can imagine, as the wave passes, each one of those white bobbers rises and falls with the wave. And so the more bobbers you put in a row, the more energy you capture as each wave front passes. Looking at the upper right, Ocean Energy Limited out of Ireland is a completely different technology. This uses the oscillating water column. And so if you look, let's make sure, if you look here, you can see this silver column. That's actually an air turbine. And what happens is each wave passes, it raises and lowers the water level inside of a chamber. That chamber is open to that tube, which is actually a turbine. And so what happens is the wave comes in, it rises the water level, which forces air out of that turbine. And as the wave recedes, it forces air back into that turbine. And so while it does use the waves as its main energy source, it actually uses the moving air from the wave to drive an air turbine. So again, very, very different ways you can capture energy from waves that are being explored globally. Looking at Asia, I give a really interesting example from China that just sort of shows, again, the scale of the machinery that we're talking about. Here you can see the process of deployment of this device in China, where it starts in the upper left on land, it is floated out to sea, and then it is sunk to the appropriate depth. And so you can see those 3 stages outlined fairly clearly. Looking in the bottom right, you can see a concept in Korea, which is known as an overtopping device. The waves crash over the top, and there's a spiral network that forces the water in a spiraling motion down through the center of the buoy, and there's a turbine there that can be used to extract energy from that water. Looking in Japan, there are again similar, very broad range of industries involved, or converters, but of really importance is the industrial support in Japan. So as I mentioned in the previous slide, Kawasaki Heavy Industries was investing in the tidal energy, and we see that Mitsubishi Heavy Industries is quite interested in the wave energy. So much like in Europe, in Asia, you're seeing some of the large, heavy-duty engineering firms starting to put their significant resources behind the development of these devices in the industry at large. Looking at some additional marine energy sources that people may not be quite as familiar with, the first one I would share is what's known as ocean thermal energy conversion, or OTEC. This type of energy conversion takes advantage of the difference in water temperature between the surface and depths up to 1,000 meters below the surface. In the upper right, you see a map of the temperature differences at similar depths. And so you can see that off the coast of Indonesia, off the coast of the Philippines, and off the coast of Australia, you have a temperature difference of more than 24 degrees Celsius between the water at the surface and the water near the bottom of the ocean at 1,000 meters. And so that temperature difference can be utilized for a number of purposes, including electricity, desalination, aquaculture, and it can also be used for air conditioning with that cold water that's being brought up. So this is another important part of the marine energy sector. I talked about tidal energy. Some other current energies that you can use include currents in the ocean, and that I think is one of North Carolina's strongest resources. We'll talk a little bit about that. The Gulf Stream is quite close here off the Outer Banks and represents a tremendous amount of energy potential if you can capture that ocean current. Another interesting source would be rivers. Many companies, including my own, are looking not only at tidal energy development, but also river energy development. You can imagine the technologies for tidal and river are quite similar, with the main difference being there's no change in flow direction. So in the river case, you have the flow always moving in one direction. In the tidal case, your device has to either pitch or yaw to capture that energy in both directions. And then another potential source is canals. There are quite a few irrigation canals, et cetera, that move around the world. That moving water can also be turned into electricity. So hopefully that provides an overview of some of the technology that's happening both here in the US but also globally. I want to move now into some of the test facilities that we have both here in the US and globally. As you imagine an emerging technology like this, test facilities are critical as companies take their technology from idea into prototype and on to what we would consider the commercial product. Looking at here in the US, the United States has established 3 national marine renewable energy centers. I provide maps here of the 3 of them. Actually, Gabe Alsanis in the back here is from the Southeast National Marine Renewable Energy Center, which is associated with Florida Atlantic University. You can see on the upper right corner a map. Fort Lauderdale is shown, and the squares represent segments of the outer continental shelf. The small green squares represent pieces of water that FAU and SNEMREC have licensed. The first site to be developed is here on the left, the westernmost L that you see there. And so they'll be testing technologies in the ocean current because the Gulf Stream is quite close to the coast of Florida, similar to here in North Carolina. Looking in the Northwest, we have the Northwest National Marine Renewable Energy Center. It's a partnership with Oregon State University, the University of Washington, and the University of Alaska. Their main focus, as you can see, is on all 3, wave, tidal, and river currents. The river current work is done mostly in Alaska. The tidal energy is mostly done in Washington, and the wave work is done off the Oregon coast. You can see in this map that Oregon has proposed 2 test sites, the North and South Energy test sites, that will enable wave energy testing right off the coast of Oregon. And finally, you have the Hawaii National Marine Renewable Energy Center, who focus mainly on the testing of wave and OTEC devices. And you can see on the stars where some of those actual locations are in and around the state of Hawaii. Looking outside of the US, there are 2 main test facilities that really represent the sort of state-of-the-art in testing in the world. Up in Nova Scotia, you have the Bay of Fundy and an organization called FORCE, or the Fundy Ocean Research Energy Center, or Research Center for Energy, excuse me. The maps show you exactly where that is in Nova Scotia, and the inset shows you where in the Minas Passage the site will be for the testing of tidal turbines. Looking in Europe, there's an incredible test facility in the Orkney Islands known as EMEC, or the European Marine Energy Center. You can see in the inset they have a number of testing sites that they operate. You have a full-scale wave and a full-scale tidal site, and in that case I mean of the device. So if you had a full-scale device, you could go to one of those 2 sites. If you had a scale model of your device, let's say a 1/10 scale that you wanted to test, they offer scale tidal test sites and scale wave test sites. So that gives you a little sense of some of the testing facilities that are available globally. An important piece, and I won't harp on this for too long because it generally puts people to sleep, but standards and conformity assessment are an incredibly important step in the path from research and development to commercialization. So I would just like to highlight some of the activities that are ongoing internationally. These are being done under the IEC, which is the International Electrotechnical Commission. TC 114 was set up to examine technical specifications and their development for the marine energy industry specifically. We have about 10 active project teams. I provide a website here for those who are interested to see some of those details. And part of why I'm here in North Carolina this week, actually, is that the United States Technical Advisory Group held our annual meeting on Jeanette's Pier yesterday and today. And so thanks very much, obviously, to Billy and CSI. We brought about 20 experts from around the US for our annual meeting here. And again, that's sort of what brings a number of us here today. So I'm glad to be able to share this a little bit in conjunction with sort of the larger marine energy sector. Looking the next level, what standards really do is provide something to verify against. And that verification we often call certification. And most robust, mature industries have a certification track. The light bulbs in this room have been certified. This has been certified. Your computers have been certified. Your wireless network has been certified. And so this is a very important step in the commercialization of marine energy, is certification of renewable energy devices, specifically tidal and wave devices. And so a new certification system has been started for renewable energy called the IECRE. These are based on international standards and will enable the third-party verification of things like performance, reliability, safety. And I think the final bullet really sums it up. Ultimately, for the industry to be successful, we need to reduce perceived risk, and we need to increase confidence with stakeholders, investors, insurers, etc. Standards and certification are the most effective way of reducing risk and increasing confidence as an industry grows towards commercialization. So now moving to North Carolina. I'm right on time. I'd like to talk a little bit about some of the ongoing research that's happening here at the Coastal Studies Institute. I'm not sure how much people here know about it, but there's some really tremendous research going on here in the state of North Carolina. I'll talk a little bit about the resource that we do have here in North Carolina, and then as I mentioned, I'll end with just a little discussion of some of the opportunities that are available to North Carolina in its participation in the global marine energy industry. So I apologize if some of this is too simple and that if everyone already knows about the Coastal Studies Institute, but I thought it might be worth especially for people who are streaming this online who may not be familiar with the Coastal Studies Institute. There are 5 main research focuses of the Coastal Studies Institute, and I highlight the one that I think is most relevant to the work that we're doing here today, which is coastal engineering and ocean energy. And so it's very clear in the Coastal Studies Institute mandate that the development of technologies and of ocean energy in general is of key importance. And so really, again, that's why we're here. Looking at Jeanette's Pier, it is another amazing test facility that's available in the development process, especially for wave energy. Here you see the Resolute Marine Energy Wave device being tested off of Jeanette's Pier. That test was successful, and Resolute Marine has gone on to build a full-scale device that they're looking at markets in South Africa, looking at markets in Alaska, looking at other markets globally. And so Jeanette's Pier was a very important step for them in their development process. I'll say they also went up and tested a device at the facility in Duck and had some success there as well. So I think North Carolina has some real potential to support the development of wave energy given its already existing testing infrastructure. An important piece of what the Coastal Studies Institute is doing in ocean energy revolves around the, quite frankly, amazing group of universities and partners that have been established here. The main institutions would be NC State, UNC Charlotte, and NC A&T. There are a number of other universities involved. You'll see some of their logos as I go along to give you a sense of the sort of range of people that are working all together here in the state of North Carolina. They also have a number of excellent industry partnerships. Billy mentioned this technical advisory committee here at the Coastal Studies Institute that I serve on. There are a number of other manufacturers, developers, et cetera, that sit on that. And a number of the research projects that have been ongoing here in the Coastal Studies Institute are attracting the attention of large industry partners, both from the wind sector, the marine sector, et cetera. And in conjunction with that, the Coastal Studies Institute and the Ocean Energy Program host an Ocean Energy Symposium every year. The 4th of those symposiums is held tomorrow and Friday here at the Coastal Studies Institute. And I'm guessing most people know, but the state of North Carolina has made a very serious commitment to pursuing ocean energy research. And it's about the 4th year of that funding, and it's pretty clear that the state legislature is committed to this effort and is committed to continuing to fund this research. So between the great resources available, the partnerships established, and the state support at the sort of legislative level, I think those all work really well in favor, really well together in terms of what the potential is here in North Carolina. I want to share a little bit about some of the detailed research that's ongoing here in case people aren't aware of what's really happening. I'll start on the technology side. One of the really interesting developments that's come out of the Ocean Energy Project here is what's known as a magnetic gearbox. This is revolutionary change of concept in a gearbox. As most of you imagine, traditional gearboxes are large pieces of metal with teeth. Those teeth meet and they transfer load, energy, power through those teeth. There are serious problems with that, including wear and failure potentially. And mostly it revolves around those moving parts that have to interact with each other. In the case of a magnetic gearbox, while there are moving parts, they are not touching each other. And in fact, they use the magnetic fluxes of an inner and outer loop of metal to transfer torque in much the same way that a mechanical gearbox would. This research is being mainly conducted at UNC Charlotte, and if you look at some of their literature out there, they have done a tremendous job of leveraging the funding here in North Carolina to get significantly larger pots of money from both the Department of Energy and the National Science Foundation. Freedom Center is looking at grid integration issues, mostly out of NC State. As you can imagine, the integration of renewable energy onto the grid is a very important piece of the success of renewable energy. In particular, some wave devices have very unfriendly energy distributions. They're not like your conventional power plant that just turns on and runs at a steady state. These things are oscillating. Some days there are waves, some days there aren't. And so it's a very important piece to make sure that these devices and their electricity integrate to the grid seamlessly, or as seamlessly as possible. Another interesting piece of work that's being done at NC State and some other universities involves ocean compressed air energy storage. Energy storage is a huge issue in renewables. For example, at night in most places is the most windy. So you have tremendous amount of wind energy being produced at night, but the demand is at its almost minimum. You have no commercial activities, you have most people asleep at their house, and so you have an unbalance of the production of energy with the demand for energy. And so one potential solution is to store that energy until demand is at its peak, and then get it back onto the grid. So a really unique sort of research project is to look at storing air at the bottom of the ocean. And that compressed air contains a tremendous amount of energy. When you need it, you can release that compressed air back to the surface and drive an air-based turbine. And so there's work being done on how you anchor these large objects underwater and how you demonstrate them. And so there's ongoing work to sort of prove the viability of storing air at the bottom of the ocean for later use during peak demand periods. Looking at the modeling side, modeling is a critical piece of this industry as we develop. As I mentioned, the cost of being on the water, the cost of machinery, et cetera, warrant significant modeling before you undertake any on-water operations. Looking at work that's being done at A&T, NCA&T, they're looking at some turbulent wake studies. So as you can imagine, in a rotating machinery that's extracting energy, there's a wake behind it. By wake, I mean a region where the velocity is moving more slowly than it would have otherwise. That wake has all types of potential to interact with additional machines. It may change some of the fish behavior if they notice a sort of, quieter region of the flow. And so accurately capturing those wakes through numerical modeling is a very important effort that's ongoing here in North Carolina. Also, a really innovative concept known as smooth particle hydrodynamics is being examined, that instead of using the traditional CPU of your computer, it actually uses your graphics card to solve the problem. So it's a really innovative and unique piece of sort of modeling research that's being done. Further modeling is to sort of, as I mentioned, it's called this modeling and observation system, which is really making sure that what you model matches what you observe. And we use the term validation, calibration, but you need to make sure the model is grounded in reality. And so what we want to do is combine direct measurements of things like the Gulf Stream or of the turbulent wake, and then compare it with the models to make sure those models are accurately predicting the physical reality. Looking at some of the actual details of market penetration, how do you actually get renewable marine energy to the grid? First and foremost, it has to be economically competitive. So there's some ongoing research here in North Carolina to attempt to quantify the cost effectiveness of this energy, identify pieces that are the cost drivers, identify pieces where significant increases in, let's say, scale of production could really dramatically reduce the cost of these devices, which is going to be the critical driver of large-scale market penetration, is cost competitiveness. As I mentioned, environmental impact is a huge issue. There's an ongoing research study to look at the sargassum algae colonies that are out in the Gulf Stream. It's a very important part of the ecosystem, and it's unclear what the extraction of marine energy would do to that community. And so there's ongoing efforts to try to understand how that macroalgal ecosystem would be affected by the extraction of energy from the Gulf Stream. Finally, there's a huge piece which is public acceptance. It's very important to have the public and the local community buy into what you're doing, believe in what you're doing, trust that you do care about the environment, trust that you're not looking to cause harmful side effects to a beautiful ecosystem, for example, the Outer Banks of North Carolina. And so there's a number of universities that are collaborating together to understand community support for renewables and obviously focusing on the coastal North Carolina perspective. And they've been doing a series of surveys, a series of consultations, interviews, trying to understand the public's perception so that we can try to get the right message out to ensure that the public is on board with this type of renewable energy. And so finally, the resource itself, which I think is quite critical here in North Carolina. And so the first big one is the Gulf Stream. It is massive, it has a tremendous amount of energy, and it is quite close to the coast of North Carolina. And so we right now have a couple different research projects going on here in North Carolina to try to quantify that resource. Specifically, some of the researchers are taking what are known as stationary acoustic Doppler current profiler measurements, or ADCP measurements. This ADCP is a device that can measure the water velocity over a large extent from near the surface down towards the bottom. This allows you to characterize the Gulf Stream, and so that assesses the available resource. Also here in North Carolina, as I think everyone knows, you have a tremendous wind resource, and because of that, you also have a tremendous wave resource. And so there's some ongoing work to quantify the North Carolina Atlantic Ocean resource, both looking at offshore wind and wave devices. And as you can see, it's a combination of wave data from available sources mixed with some modeling activities to try and really quantify that resource. And as you can imagine, in the project economics, the available resource is another driver. You need to have a very strong, viable resource if you're going to put in the time and effort of deploying these marine energy devices. So this resource assessment and characterization is very important work ongoing here in North Carolina. And so yeah, just to finish up, a couple sort of perspective points. I apologize for reading, but I'm going to. I think one of the most important potentials that North Carolina has is in its intellectual capital. This state has an extremely strong educational infrastructure, and as I'm inherently aware, and many of my colleagues are, emerging technologies need innovation. Innovation is best done in the university, in a research lab, in a facility where you have the space to do that innovation. And so the infrastructure here in North Carolina really provides for that innovation. Looking at expanding the manufacturing capabilities, this is a global industry. The technology and the components to make this industry work can come from anywhere. And so there's no reason that North Carolina could not provide the technology, the components, the know-how, even if they don't have the tidal energy resource per se here. They can still be a dominant player in the tidal energy industry. A really good example of that would be Germany. Germany has almost no tidal energy resource. However, they've made it very clear that they would like to be a global leader in the development and export of tidal energy technology. Looking at commercialization, I really think that coordinated multidisciplinary research ongoing at the universities is a key piece that will actually support and drive commercialization. Because as I mentioned, it's something that a private company cannot do. They do not have the financial or manpower resources to do that kind of really cross-cutting multidisciplinary research. Looking at the maritime infrastructure here in North Carolina, it's another really important piece. We're here at a coastal community. There's a tremendous amount of on-water experience, invaluable. People who know how to work on the water are more valuable than you can possibly imagine when it comes to deploying a tidal energy turbine, a wave energy converter, etc. And it's an incredible resource that you have here in the coast of North Carolina, is that experience, the hands-on know-how. You have the equipment and vessels, and I think you could really capitalize on some of that existing supply and maybe even look to expand some of that supply, which would tie back into some of that manufacturing capabilities. And again, I think while you may not have a resource in tidal energy, it's no doubt that you could be a leader in things like the construction of tidal energy devices, training of personnel to operate, to maintain, to deploy those devices, and there's real potential to do testing here in North Carolina, as I mentioned at Jeanette's Pier and at the Duck facility, and potentially some others as we go forward, and as the program expands here in North Carolina. And finally, obviously the big one is electricity. And North Carolina does have the real potential to produce electricity from marine energy. And I provide what I think of in my crystal ball, gazing in the distance. In the near term, I think what you're going to see are going to be demonstration scale wave energy devices. I think you're going to see offshore wind turbines. And I think it would behoove North Carolina to look at some hybrid systems, where off of the tower of the offshore wind plant, you have wave converters. It has a number of advantages when you start to make these hybrid systems that take advantage of a single mooring point, single vessel, etc. Looking a little bit further forward, next decade maybe, I think that North Carolina and much of the southeastern U.S. seaboard has a real opportunity to start deploying demonstration scale Gulf turbine or Gulf Stream systems. It would be the first ever demonstration of an ocean current device, and I think North Carolina and Florida right now are sort of poised globally to be the first to really experiment and demonstrate the viability of ocean current energy. And I think this energy storage concept has some potential in the longer term to be demonstrated here in North Carolina. Again, I think these are longer term images. And in the far forward, I think we could all dream of arrays of offshore wind farms and arrays of wave energy converters. That's the long-term goal, and I think that would be proof of the commercialization of this industry, and I think you'd see that levelized cost of energy would actually start to drop to more on par with some of the conventional sources of energy that we're using today. And finally, again, I think North Carolina can support commercialization. You'll see that it's sort of a theme on this slide. And that's really what I think North Carolina should focus on, is how can we support the commercialization of this industry. And so from the electricity standpoint, if you get devices in the water, we need evidence of operational hours. How long can these things last between maintenance? What type of service intervals do we need? What type of vessels do we need? All of this is going to come from real hands-on deployments and actually producing electricity. And so hopefully that's another piece of the puzzle that North Carolina can support, is through that actual production of electricity. So I need to thank some of the sponsors that Verdant has had in the development process that we've gone through. Through the Department of Energy and through NYSERDA, which is the New York State Energy Research and Development Authority, we've received a significant amount of money to advance our technology, to advance the RITE project. And specifically, we've been able to partner with the St. Anthony Falls Laboratory at the University of Minnesota, the National Renewable Energy Lab in Colorado, Sandia National Labs in Albuquerque, New Mexico, and then the Oak Ridge National Laboratories, which is in Tennessee. And I provide a website on the bottom. This is a DOE-provided website. It's called Open Energy Information, or OpenEI. They have a tremendous amount of information about the industry, about technologies, about how it works. And so if I've piqued your interest, certainly here's a website that you could go to learn more than I was able to present, obviously, in the 45 minutes I had. And so with that, I will say thank you very much. It's been my pleasure to be here today. My contact info is here, cell phone, email. I love talking to people about what it is I do, what we do, the future of this emerging industry on the globe. And so yeah, thank you very much.